Hi there, my name is Sarah. I'm so sorry that I couldn't be here live today, but I'm so happy to have the opportunity to speak with you through the magic of technology today. A little bit about myself before we get started. My background is a mix of software engineering and working with everything geospatial. Currently, I head up the developer relations team here at Planet Labs, where I get to play with satellite imagery every day. So now let's learn about geospatial raster data. Today I want to give you just enough knowledge that you feel a bit more familiar with core geospatial raster data concepts. I don't expect you to walk away from this talk knowing everything. Really, I just want to equip you with a foundation that you can use to inform your Google searches when you begin working with geospatial raster data. I'm going to start with a brief introduction to just general geospatial concepts, and then we're going to talk specifically about raster data and concepts related to working with that kind of data specifically. So let's start with those core geospatial concepts. If you and I have ever spoken together in real life before this, you've probably heard me say the phrase, spatial isn't special. And that's really true. Here on the left, I've got a table of data. This data just happens to be showing a bunch of fire stations in Austin, Texas. I live in Austin, Texas, so whenever I'm looking for free data sets, I always tend to just go to my city's GIS website and look for data. So you're probably familiar with data that looks something like this. You've probably opened this kind of data set in a spreadsheet or something similar. It's basically just tabular data. Now on the right side, I have a table of the same data showing fire stations in Austin, but here I've added two columns which contain longitude and latitude values as x and y coordinates. And that's really the only difference between these two data sets, but it's a really important difference because those two columns make the data set on the right spatial. Now you can think of spatial data as putting a where with a what. That table of data on the left in the previous slide that showed you fire stations, that's the what in the scenario. The spatial data that we saw on the right, adding locations with latitude and longitude coordinates, that's putting a where to it. So here this picture is a visualization of the spatial data that was on the last slide. Here we've basically taken those x and y coordinates, the latitude and longitude values, and we've plotted them on a map. The plotted locations let us visualize where all the fire stations happen to be in the city of Austin, so we have put a where with a what. When you're thinking about things that have a where with them, a where associated with them, many of those things can be represented by a point, a line, or a polygon. For example, on the previous slide, those fire stations were represented as points. Now think about a map showing roads through a city. Those roads might be represented as lines. And then think about a map showing, for example, every swimming pool in the city of Austin. Those swimming pools might be represented with a polygon that shows their rectangular or irregular shapes. Now, all of these kinds of data, when the data is represented as points or lines or polygons, are what we call vector data. There's two categories of geospatial data to be familiar with. Vector data is one, and raster data, which I'm going to talk about soon, I promise, is the other. I want to briefly show you some of the most common file types that you're going to encounter when you're working with geospatial data. Here in this list, the first three file types are for vectors. So GeoJSON, shapefile, and KML, these are all file types you might encounter if you're looking for point, line, and polygon data. And then JPEG 2000, GeoTIFF, and Cloud Optimized GeoTIFF, or COG, are data types for storing raster data. Most commonly, you're probably going to encounter GeoJSON or shapefile for vector data and GeoTIFF or COG for raster data. So now let's talk about how we talk about location. Defining location would be a whole lot easier if the Earth was flat. You remember from geometry class long ago probably, if you want to locate a point on the surface of a plane, for example a point on a piece of grid paper, you're going to use x and y coordinates to define that point. If you want to talk about elevation, you could absolutely also add a z-coordinate, which would tell you how far up or down from the surface of the plane that point is. And when you're working with geographic data, you can apply same geometric concepts that we talked about on the last slide to geographic space. We do that with what we call geographic coordinate systems. Here, a geographic coordinate system is what allows us to map any point on the surface of the Earth. In this case, we use latitude and longitude values to map those x and y values. X and y coordinates on the surface of the Earth are just called latitude and longitude. Optionally, we could also include an elevation or a depth with a location on the surface of the planet. Remember how I said everything would be so much easier if the Earth were flat? Since the Earth is not flat, we have to translate those two-dimensional geometric concepts into three-dimensional geographic space, or vice versa. So to map a location on Earth in a two-dimensional space, like your computer screen or a paper map, it's necessary to convert a location using what we call map projections or projected coordinate systems. A projection results from taking geographic coordinates and applying a special kind of mathematical function to them, which converts them to coordinates in flat space. Now, there's a lot of map projections that can be used in a lot of different ways. Basically, because 2D space is never going to be equal to 3D space, every map projection is going to have to find a balance and strike a balance between different trade-offs that you make during the conversion process. So the projection that you choose probably depends on what your end goal is. But just to give you an idea, Mercator or Web Mercator is probably the most common projection that you're going to encounter. Also, I highly recommend this XKCD comic if you want to go read about map projections with humor. So that was really a whirlwind tour of some foundational geospatial concepts. At this point, if the moderator wants to take any questions, we can pause a moment here. Otherwise, let's move on and talk about raster data. So previously I told you spatial data isn't special. I didn't lie to you, that's definitely still true, but there are still things to take into consideration when you're working with spatial data. So even though spatial data is just so-called regular data, but we've added location information to it, still when you're selecting tools to use for working with the data, you should keep in mind that spatial data usually is going to require some spatial data tools. Some characteristics that are special or unique to spatial rasters that you should take into consideration when you're going to work with rasters includes raster data can be multispectral, raster data can be spatially referenced, and it can include spatially relevant metadata. So when you're looking for tools to work with this data, you want tools that can deal with all of those characteristics. Also earlier I told you that data can be represented as either a point line or polygon that we call a vector, or a spatial image called a raster. It's also important to know the type of the data you're working with because that's also going to inform the tools you use to work with that data. Now let's talk about what exactly an image or a raster means in its context of geospatial data. So here on the left, you see a region that's represented with points that connect into lines that then draw polygons. On the right, we're representing the same region, but instead on this side it's represented by a grid of squares, and each square has a discrete value. In this case, the color red is a value, the color green is a value, and the color purple is a value. In a raster image, we call these squares pixels, and each pixel holds a discrete value. In spatial raster data, square pixels are arranged in a two-dimensional grid. Pixels that represent the same value on the surface of the Earth have the same numerical value. In the example grid here on the left, every pixel represented by a 2 has the same value in whatever that pixel is representing on the surface of the Earth, but same for values 1 and 3. On the right, though, I've actually zoomed into a real raster image, and you can see the grid of pixels that are in that raster. So I'm going to take a minute now and talk about resolution, because when you're talking about rasters in a geospatial context, unfortunately, you're probably going to hear the word resolution used a lot, and it's used to mean different things. It's a bit of an overloaded term in raster geospatial data. So resolution can be used to mean talking spatial resolution. The spatial resolution of a raster is the ground area covered by each pixel. Basically, if we're talking about 3 meter spatial resolution, then every pixel in that raster is going to represent 3 meters square on the surface of the planet. But we might also talk about temporal resolution, which is the frequency between image captures. So this is used especially in Earth observation. You might revisit areas on the surface of the Earth repeatedly in order to recapture imagery. So we talk about that as temporal cadence or temporal resolution. Resolution can also refer to an image's spectral resolution, which is basically how wide a range of wavelengths in the electromagnetic spectrum that image can represent. And then finally, the radiometric resolution of an image is how we talk about the bit depth of the pixel values, or how wide an array of values each pixel can represent in that image. So if we say a raster has 8-bit resolution, that means it can represent up to 256 unique values in each pixel. I want to take a minute and expand specifically on the idea of spectral resolution, because this is probably one of the most important resolution types to you here today. So the sensors that capture Earth observation data and produce raster images can capture data from a wide range of the electromagnetic spectrum. Images that include more than one part of the spectrum are called multispectral. So here, let's take what we might consider a regular old visual image, like the picture you see on the right side. By the way, this is just an aerial satellite image of San Francisco from a couple years ago. So let's think about this image in spectral terms. Looking at it, we know that the data is going to be made up of red, green, and blue values. If you're familiar with the idea of visible light, then you know that red, green, and blue makes up all the colors that we can see with our eyeballs. So as a geospatial raster, this image will be said to have 3 spectral bands. You could think basically of a raster band like a layer. So spectral bands or layers here are red, green, and blue. Those bands add up together and they create the visual image that we see on the right side. When I talk about bands or layers, think of each band as being its own discrete grid of pixels. So the pixels in the red band only represent how much red is in each area of that image. Same for the green and blue bands. When we put them all together, that's how we get a visual image like the one on the right. So one of the really cool things about geospatial rasters is that we can work with and manipulate each of these spectral bands independently. So maybe you want to work only with the red band here, or only the data in the green band. Or you could take the red band's data and combine it with the blue band's data and remove the green band data completely. But there's more than just red, green, and blue light in the electromagnetic spectrum, and there's more than just red, green, and blue spectral bands captured by imagery sensors. Sensors that capture visible light, they can produce red, green, and blue bands, but outside of the visual range, we can also make spectral bands of near-infrared, shortwave infrared, panchromatic, and other data. All of these spectral bands, and a lot more, are commonly found in Earth observation data like satellite data. So that's all a very gentle introduction to general geospatial concepts and some key points that you should know about geospatial raster data. Some points that I hope you take away with you today include that data with location information attached is what we call geospatial. You might also hear spatial. We basically use those words interchangeably, so you might hear both. Spatial data is represented as points, lines, or polygons, and we call that vector data. And a spatial image made up of pixels arranged in a grid is called raster. A raster can have spatial, temporal, spectral, and radiometric resolution values. And finally, a multispectral raster means that it has more than one band of data. So that's it for me. I think there might be people on now who are available to take your questions, so if so, reach out to them in whatever method they told you to use. Also, though, I'd love to hear from you. My contact info is here. The slide links are also available for you to see at this link. I think the link to the video will also be shared by your hosts, and thank you all and have a wonderful day.